Good morning, everyone. So welcome to this month's IAA seminar. So it's my great pleasure to introduce Dr. Alfred Chen, who is a good friend of mine and work on very interesting research of autonomous vehicles and security. Alfred is an assistant professor of computer science at the University of California, Irvine, and his research interest spans over AI, system, network security, and his most recent research mostly focuses on AI security in autonomous driving and intelligent transportation, and his works have high impact in both academia and industry with 30 plus research papers in top tier venues across security, mobile system, transportation, software engineering, and machine learning. And he has a national US DHS US Cert Alert, multiple CVEs, more than 50 news coverage by major media like Fortune, BBC, and also vulnerability report acknowledgement from US DOT, Apple, Microsoft. So it's a long list. And recently his research triggered like 30 plus autonomous driving companies and V2X standardization workshops start security vulnerability investigations, and some confirmed work on fixes. He co-founded the famous AutoSec workshop, which is co-located with NDSS. I like it very much, and I tend to attend like every year, and also co-created the famous DEF CON's first auto driving themed hacking competitions. He received many awards, including SF Korea, ProQuest Distinguished Dissertation Award, UCI Channel Award for Mentoring, and he received his PhD from University of Michigan in 2018. Without further ado, so we'll head over to Alfred to give the talk.
Sure. Yeah. So thanks a lot for the introduction, and then I assume you guys can hear me well.
Yes.
Okay. Sounds good. Okay. So yeah, it's definitely a big pleasure to speak here, and then I think Inju did a very good introduction of my background. So I guess for today I'll share a bit of experience and lessons we learned from the past few years that we look into the AI security problem in CPS, especially those highly safety critical ones like autonomous driving. So I also had a little bit of introduction of myself. I guess this is my first time to speak to this institute. So I guess like Inju said, I'm an assistant professor of computer science department at UC Irvine. So I've got a PhD from Michigan. So my group's name is S-Guard, Autonomous and Smart Systems Guard, with the grand vision of securing the emerging technologies that make our whole world more intelligent and also more autonomous. So the core expertise of my group is AI system and network security, mainly in the context of mobile CPS and IoT, basically those needs integrated consideration of both cyber and physical aspects. So in general, I'm just interested in any security problems that of, computer technologies that are of high criticality to our daily life and society. And this is exactly why I focus on self-driving and transportation AI security since I joined UCI. So in my group, so besides publishing papers, I guess we also try our best to generate the practical impacts. So for example, we usually make demos for the attacks that we created. We deploy to the vulnerability management agencies like CVE, US CERT, developers like Android, Linux, Apple, Comcast, Microsoft. And because recently we also look into autonomous driving problems, so we also have interactions with the those vehicle and also autonomous driving companies and US DOT. So my research so far in this problem space can be classified to 5 general categories: CPS, AI security, network security, UI security, access control policy enforcement, and side channels. And today I will be focusing on essentially the most recent interest of my group, essentially CPS AI security, which is a relatively new area, right? Because it's actually a combination, at a very high level, a combination of AI security, which starts at around 2013, and the great penetration of AI in real-world CPS systems. For example, in this figure for the automotive industry, roughly from 2015. And for today, this trend is even more obvious with all these AI-enabled autonomous systems coming into real life, right? Cars, drones, and robots. So for this kind of systems, right, it's definitely very desirous to study their security, right? Because very obviously they are highly safety critical in terms of their decision-making process. In this case, it's actually a very unique chance for security people to have a very high impact on public safety and also society, right? For example, if you look at this fatal crashes of Uber and Tesla, right? And on the right, it's actually in California. So yeah, a lot of high impact, high profile like issues that can come out of the security problems if we study them. So in this problem space, my focus is mainly in the automotive and the transportation domains. More specifically, there's two very prominent technologies. If you like watch headlines, right? So for example, on the left, this is autonomous driving or AD, like which make cars drive by themselves. And on the right, this is V2X, based intelligent transportation, which is essentially a vehicle to everything. They try to generally connect cars and also the infrastructure and also the other cars and pedestrians. Just make essentially, if you look at this, this is like on the left, this is the autonomy stack of transportation. On the right, this is the networking stack of transportation. So for both technologies, there are a huge number of companies behind them, and then also government. So yeah, definitely a lot of technology advancing in the recent years. So so in today's talk, I'll be mainly focusing on the left side because actually my research has been doing things on both sides, but then today I'm mainly focused on the left because this is also the main focus of my group in the past few years. There are a few reasons. So the first reason is that this is probably the fastest growing AI-enabled autonomous systems in industry today, like cars, right? You can see actually more than 60 companies are testing their self-driving cars in California today, actually. And then among them, a few of them, if you know, then essentially like so Waymo and also GM are already getting the permit to charge customers for their self-driving taxi services. And the second thing is that this is definitely a very highly, very safety critical system, right? Because cars are different from drones, from robots. Cars are very unique in terms of that they are heavy, they're fast moving, and also operating in public spaces, which make their security problems especially safety critical. And last but not least, cars are, especially the driving problems, are highly complex to get right? So because you need to drive, but also you need to drive so following the policies and the rules, right? It's not just like, okay, as long as I'm not crashing into people, crashing into the rules and infrastructure, I'm fine. You also need to follow traffic rules, right? So which means that you need to handle not only weather conditions, lighting conditions, road and traffic conditions, but also you need to be safe, of course, and also complying to traffic rules, right? So a lot of complex considerations, and then when we see something like this, usually that means a lot of chances for like attackers to make something wrong. Okay, so to start with, I'll start with some background. So this is probably at 10,000 feet, right? So essentially, self-driving cars, like you put a lot of sensors onto cars to make them drive by themselves, and then this sensors essentially tries to perceive the physical world, right? Like the road, like cars, like traffic horns, stop signs, traffic signs. And in the industry-grade AD systems, so usually this the sense information will be goes through a modular process, right? Perception, which you see the surrounding obstacles, localization, which you know where you are on map, and then prediction, you predict where the surrounding obstacles will go in the future. And in the end, you will do a planning, right? With all this information, you want to make a correct and safe driving strategy for yourself. So on the right side is essentially many people call it like autonomous AI stack, right? Because this is AI for autonomy, right? So then once we get the trajectory from the planning module, then we get it to the control, and then it gets back to the physical world, right? It's a closed-loop control system. So then now with this system architecture, we can look at it from the security point of view, right? So if we want to affect this autonomous decision-making process, which is pretty much in this red blocks, what we can do, right? So one way you can do is to attack the sensors, right? Because they are the fundamental source of information for this autonomous driving, this autonomous decision-making process. Then with that, essentially you can definitely so easily change or have the chance to change the decision-making process. So in this particular case, right, for example, if you look at this, all these 5 representative sensors that I showed in this slide, jamming and spoofing attacks have been discovered on all of them, actually, in the security community. It has been demonstrated with demos and real sensor devices. So besides sensor attacks, there's another way to fundamentally change or fundamentally influence the autonomous AI decision-making process, which is changing the physical world, right? Because if you do that, even if your sensor is all correct, it's behaving all right, then if you change the physical world, the information flow can also be fundamentally altered, right? In terms of driving this this AI decision-making process. So in my work, I consider both. Okay, so in this problem space, right? If we look back, right? So the earliest work to study this autonomous AI security probably dated back to around 2015 and 16. So basically, those are the time that people focus on the sensors because that's the most mature parts at the time. So basically, there's some work in Black Hat and DEF CON. They try to target the sensors in production AD sensors like Tesla. They try to use the sensor spoofing and the jamming, and what they see is that they're able to make obstacles disappear or spoof fake ones, right? So for example, these are the screenshots from their papers. As you can see on the left, I believe this is ultrasonic and the radar. On the right, this is this Mobileye. They are able to make obstacles disappear or spoof the fake ones. So then, for all this works, they just look at the sensors, right? They want to trigger some artifacts, some unexpected behaviors of the sensing mechanism, but they didn't take a close look at the AI side, right? Essentially, as you can see in this diagram, there's a lot of new components has been developed today to enable high-level autonomous driving, like level 4. So on the AI side, right, before my group started working on this direction, so there's a famous lab work, I believe many of you know it, which are basically those works focused on stop signs or traffic signs. So basically what they do is that they take a state-of-the-art this camera object detection model. They try to use some malicious stickers or posters to trigger a misdetection of this traffic sign, right? Especially stop sign. For example, these are the figures they got from the previous works. On the left, this is adding stickers to make a stop sign disappear. On the right, this is a spoof fake one, right? Which doesn't look like a stop sign. And then very recently, so earlier this year, people are able to show that this kind of attack is actually working on commercial vehicle systems. So this is the video I get from ADSS work earlier this year. So basically, as you can see, there are some of this some dirty patterns on the surface of the traffic sign, and they are able to trigger inconsistent detection results actually from a commercial vehicle system. So sure, in this, if you look at all this works, right? So missing a stop sign is definitely very undesired. But then if we think about it, right, it's also not the worst case, right? So because even if we miss a stop sign, we also have many other components in the system that can prevent me from crashing into these obstacles, right? So at least I'm safe, right? So sure, I violated the traffic rules, but then I'm not having a crash, right? Because there are also so especially this road obstacle detection systems, right? To avoid those collisions. This is why when my group started looking into this direction, we took a more extensive look at all these kind of AI components, right? So because if we look at this diagram, there are so many of them. And then, for example, here, all these yellow boxes are from my group. And then, as you can see, we pretty much, in the past 3 to 4 years, we look at pretty much all of them. And also, these are also only for the design level, right? These algorithms are by design having problems. So besides this, we also look at the implementation level problems. For example, like software bugs, which is published in software engineering conferences. So for this work, so many of them, especially those ones that I show in this slide, they are essentially the first to look at the specific problem like formulation, and then also they generally publish in top tier places across security, machine learning, and software engineering. So basically, for all these works, they all have some their unique like problem definitions and also their domain-specific consequences. And then they also each of them come with different insights, right? So for example, many of them are talking about this how to like trigger this AI vulnerabilities, and some of them are about this algorithm design flaws. Many of them are about this coding errors, like software bugs, right? So somebody make mistakes in the coding. So obviously for the sake of time, I cannot cover all of them, right? So even though for each of them, they definitely still deserve a whole talk to talk about the insights. So but today I will just more talking about this a few more general learnings we get from this journey, right, in the past 3 to 4 years with all these different trials. So basically, I will talk about two levels. One is the technical level learnings, and another one is more looking back at more high level at the area, right? So what are we doing? So for each of these levels, I will talk about two key learnings, and then on the technical level, I will mainly talk about first about sensor fusion, right, which is something many people believe to have potential for security. And also the second one is about adversarial AI, right? So how does the driving context play with adversarial AI? So let's first look at the sensor fusion side. So basically, so in this when we study this kind of all these kind of works, this is one of the works that about sensor fusion, which is published in last year about SMP, which is the top tier security conference. So before we get to that work, right? So even my group has many trials in this domains, but then they generally just focus on one sensor, right? So for example, for this ones that I showed before, they generally only focus on like either in this case like a camera or our own work, right, which is probably CPS and Usenet security. They just focus on the LiDAR, and also there's some works on Tesla just focus on the camera, right, like projecting a human figure onto the ground. But then if we look at them, right, so then we look at the industry-grade AD systems, then we find out there's a clear gap because all these prior works are limited to attack on a single source of AD perception. For example, camera or LiDAR-based AD perception like alone. But then if for all these works, if you look into them, they all say, okay, let's use sensor fusion. So basically this MSF or model sensor fusion is already recognized as the general defense strategy against these attacks on the AD perception. So this makes sense, right? Because if you have multiple sources, you can do cross-checking, right? So that in that case, at least you are able to find some inconsistency. So, but then because of this common belief, right, we also want to investigate that whether that's indeed true in the particle settings. So that's why for this particular case, we performed the first study on the security of MSF perception. We want to directly challenge this security design assumption by exploring the possibility of effectively and simultaneously attacking all these perception-like sources. In this particular case, we try to attack camera plus LiDAR because that's the most common combinations, right? So they are complementary in terms of their features. So in this case, we use a new attack vector, which is a maliciously shaped 3D object, right? We call it adversarial like 3D objects. For example, like a traffic cone or rock, right? You're able to do shape manipulations on top of it. So the benefit of it is that if you use this maliciously shape, it's able to simultaneously influence both camera pixels and LiDAR point cloud, right? Because if the shape changes, the pixel around it will also change, right? It will so infect the image or camera-based perception. And of course, if you change the shape, it will influence the point cloud, right? So one way to exploit this is to put this object in front of the car and then try to fool the victim to detecting it and crash into it. And then this particular idea can also be able to achieve a good physical realizability. You can do 3D printing, and also it can be very stealthy, right, by mimicking this normal road objects. For example, like this broken-looking traffic cone or rock, right, just simply like a rock. To do that, we also create many new methodologies. So because we want to make this a shape-based attack being optimizable through a optimization process that's differentiable. So we use many differentiable like rendering and a new differentiable this approximation function design for the pre-processing, for example, in the LiDAR processing, there are actually many discontinuous steps. For example, there's a cell level aggregation feature. Then we design new essentially so differentiable approximation of the functions. We call it a soft the functions to make it differentiable, and then which shows to be very effective. It gets from lower than 10% attack success rate to 100%. So more details in the paper, but then for today, I cannot really get into many of that details. But then I want to first get the hell of idea that's through. So the ability to make sure that everyone knows what we're doing. So essentially, want to show a demo. So essentially, this is a binary case of this attack. So this is a traffic core 3D printed. And I put in a miniature road in my lab. So in this case, it's all benign. So as you can see, it's definitely very hard to get wrong, right? So on the left, you have a very big red objects, look like a core. And on the right, there's clearly some points being blocked, right? So it's sure. And also this industry-grade AD system didn't get it wrong as well, right? Of course. But when we change to the universal case, things all change. So in this case, as you can see, after the optimization, right, we changed the shape a little bit. As you can see, there are some like goosebumps, like so on the surface of this traffic cone. And on the right, actually, the point also becomes a little bit more noisy than before. And in this case, it actually cannot be detected in both camera and LiDAR, any of these frames, right? So in this case, we just put it into exactly the same position, and then actually it's not being detected in any of these frames. So then with this, we are kind of being encouraged that I want to try it on a real car. So as you can see, this is a 3D object with a kind of a special shape, which is like a rock, right? So in this particular case, it was a cube, like a very regular cube, but after optimization, it becomes like a rock. Then we just drive it, and then we put it into the middle of this road, and then we drive forward. And as you can see, even though for human eyes, it's still very clear that on the left there are some point blocking, and on the right that's something like a rock in the middle of this road, and then it's not being detected, just like a traffic cone case. So we also have a demo website if you want to see more. All right. So and then today we are in my office, so I think actually have some of those just on my kind of shelf, right? So yeah, essentially these are kind of the sometimes once you do research like this, you get the souvenir, right? So in this case, this is this universal traffic cone with a very strange looking surface. And this is actually the rock case, and this two are actually from the same cube, but then because of the different the learning rate in the optimization process, they become very different in terms of the looking. So anyway, so yeah, if there's a chance, you guys will drop by Irvine, I can probably show you in person about this one. Okay, so then let me see. That's a question. Okay, so that's just a reminder. So okay, so then with this, right? So I guess one thing we can see security from this research is that sensor fusion-based defense can actually be fundamentally bypassed in practical AD settings, right? So in this case, camera plus LiDAR, no matter what fusion algorithms used, right? Just no matter what you use, we can attack those, right? In this case, yeah, it can be fundamentally bypassed. So then with this, right? So many of you might ask, okay, in this case, it's because it's camera plus LiDAR. You can probably use the same attack vector to attack both. Yeah, maybe that's possible, and then machine learning is vulnerable in general. So it's much harder to use the one single attack vector to attack both, right? Or attack multiple sources. So actually, I do have such cases in the ADA stack, right? So in this case, it's more on the localization side. They fuse LiDAR, GPS, and MU. So for them, it's actually very hard for you to use one physical attack to attack multiple because they are all using different the physical mechanisms, or essentially it's the medium, right? So LiDAR is the laser, GPS is like wireless like signal, right? So MU is the sensing mass like inside. So in this case it's much harder. So it is still possible, right, to break sensor fusion. So this is the work that we get in using security 2020. So this is actually the first time someone look at this multi-sensor fusion-based AD localization. In this case, it's actually not deep learning. This is the kernel filter-based. So we found out that using GPS spoofing alone, which is actually the pervasive attack vector today, still open problem, especially in the essentially this is a lot of events being discovered, being identified near the Russia area. So and then in this case, GPS spoofing has long been a problem, and many people believe that multi-sensor fusion is the way to defend against it because, of course, more sources, right, more cross-checking. But then in this case, we found that actually GPS spoofing alone can actually achieve end-to-end impact on fusion-based systems. So in this case, we found that just if you put it into the driving context, if an attacker vehicle just tailgates for 2 minutes, it's almost always, like 97% of chances, they're able to find an opportunity to break fusion and cost-effective to drive off-road or to the runway. And I also have a demo website to show that using end-to-end simulation. So the main cause of this is that is real-world sensor like noises, right? For example, MU drifting or LiDAR locator inaccuracies. So basically, this sensor noises, they are actually very frequent and also very large, so that they leave some low confidence time windows of the B9 sources. If the B9 sources are low confidence, then GPS spoofing can exploit that window, right? Because when the window, at the window when LiDAR is very, very confident or MU is very, very accurate, so actually it's very, very hard for GPS to influence the fusion results very quickly. But there do have periods that we found out that MU and LiDAR both not very confident. So in that case, GPS spoofing can quickly take over that fusion output if you just look at that window and quickly take over. So what's surprising to us is that because in the end, kernel filter is fundamentally vulnerable if some sources are untrusted. But then what's surprising to us, most surprising to us, is that even with this very high-end 80-grade sensors, these noises are still very large and frequent enough for a single tech source to exploit. Because this MU, so this LiDAR, are actually very high-end, right? So for the LiDAR using self-driving cars, they are at a time, with Valentine's dominance, it's like 75K for one piece, right? But still, right? And also MU is also high-end ones, around 10K for one MU piece, right? But still, the noise is still large and frequent enough for even one single source to practically exploit, like just 2 minutes, right? So basically, through these two works, just put them together, you can see in the first work, we are able to see that it's possible to bypass the fusion via simultaneous multi-source attack. And for the second one, is that you're able to bypass fusion via strategic or opportunistic single source attack. So I would say if you put them together, definitely you can see that we can say sensor fusion is definitely not equal to security, especially in the practical CPS settings. So if you want to use the fusion for defense, I believe that you can definitely raise the bar for the attacker, but then you have to design it carefully, right? So definitely not just to use the traditional ways. You have to design more specifically for security. Maybe the way out. Okay, so that's the first part. So basically about this sensor fusion versus security in practice. Then the second one is that I want to talk about is driving context versus adversarial AI. So for this particular case, right, if you look at so this is the work I just talked about this adversarial to the objects, right? So essentially what you are we design new methodologies to formulate essentially to model this attack vector and then to make the optimization process more efficient, more effective. And but after all, right, the high-level finding is that we're able to find some semantically meaningful corner cases for a victim CPS AI components, right? So for example, here, as you can see, because this traffic code is like a broken locating traffic code in the real world, On the right is like a rock, right? So essentially, for this AI, the CPS AI to drive in the physical world. So there are many corner cases in the driving context, and in this case, we are able to systematically discover them via optimization, right? This is essentially what we have done, right? So finding corner cases for AI that's semantically meaningful in driving. So following on that, we actually did a lot of just this kind of corner case discovery. Of course, for each of them, we did design different attack vector formulation, there's attack vector modeling and also attack goal modeling, optimization problem and formulation. But then what I would kind of put them together is that essentially that we have defined many more corner cases following this line of research strategy. So for example, for tracking, right, we also the first is study tracking. So essentially we found out that, okay, so in this case, for this kind of the taxi, they already have some advertisement, which can be used to introduce malicious inputs. Then we find out that actually this is able to move a roadside object into the current lane, causing emergency brake, or move it from car away, causing a crash. We also look at lane detection. We're also the first to look at it. So we driving around Irvine, we find out that, okay, there are actually many of these dirty road patterns, like white stands, which can be used, possibly, right? For example, in this video, as you can see, once they put these dirty road patches, carefully designed ones on the ground, this device is able to deterministically bend this lane detection result to the left, right? Well, in the binary case, it's totally straight, which means that this dirty patterns actually can be used to attack self-driving cars. And we also try this on a real vehicle, and in this case, it's actually being able to cause the deviation very quickly, within 1 second, cause this crash to this dummy, this cover this boxes. And actually, we tried it for 10 times, actually 100% crash rate for real vehicle, even with the autonomous automatic emergency braking, the AEB. We also look at trajectory prediction, and in this case, we noticed that, okay, in the real world, many drivers can drive in a very strange way, right? So, but we still think that's okay. That's why in this case, so we try to design malicious trajectories, and we found out this one can also be used to attack trajectory prediction, right? You're able to spoof a cutting trajectory causing emergency brake, or a driveway prediction causing crash. And last but not least, so earlier this year, we also looked at planning, right? So in this case, it's actually quite different from the previous ones that we studied, because this is not a DNA-based, it's a program-based. Because planning, people want more explainability and then, essentially, to make it easier to guarantee the safety than DNA. Then in this case, we found out that, okay, actually, around Irvine, there are some roadside objects around the road. And we found out that actually this can be leveraged by the attacker to cause undesired behavior for self-driving cars, right? So in this case, we use the domain customized evolutionary testing, because this is a program-based. This is no longer differentiable like DNA. So we use heuristical optimization to solve it, but still, right? We have defined that this corner cases of this placement of this roadside objects are able to cause unnecessary sharp braking, stopping, giving up mission-critical driving decisions, so on and so forth. And we also try this on a R&D autonomous vehicle. And as you can see, because this is not a perception attack, it doesn't need a special looking or a special shape. You just need one object in that specific position. So in this case, it doesn't matter if it's a cardboard boxes, traffic core. In this case, so in the real world, just use a trash can, also a box. Still, it's able to trigger this vulnerability. And we also have our website if you want to see a demo of this attack. So if we put this together, right? So I guess one thing I want to draw generally from this this kind of research, right? Of course, for each of them we design different methodology level innovations, but then if we put the findings together, basically we're able to always find corner cases in the driving context to have an end-to-end triggering of the system level effect, like crashes or denial of service. Which lead me to think that maybe the human driving environment is actually surprisingly rich of a seemingly benign corner cases, right? If you look at this, it could be a rock, could be a broken-looking traffic cone, could be like a taxi with the rear-end advertisement, could be a road set of kind of whatever kind of the objects people usually dump on the roadside, can be 30-year-old patches, right? Can be just 30-year-old patterns. But somehow they're surprisingly rich, right? So from my research in the past few years, we are always able to find there's so many like corner cases that if we look at it from human eye, we think, okay, it's a bit weird, but not too uncommon. It could happen, yeah. There's so many weird things people doing in the real street. So they're surprisingly rich, and they can be security relevant. That's the one general takeaways that we get out of it. So what we did from all this methodology is that, okay, we're able to automatically generate this kind of this corner cases, which is a good first step. For example, you can retrain the model to make it more robust, but how to fundamentally avoid these corner cases is the real challenge. So this is something I think we should be working on in the next phase of this area. So this is about my what I would highlight in the technical level. We have many other things that we find. For example, when we find that joint sensing AI design can be necessary for attacking AI-enabled CPS. Also, many times the evaluation metrics can also be at fault for the security, but I don't have time to cover them for today. And then because due to the time limit, if you're interested, we can talk about it afterwards. So on the other side, I also want to talk about some area level findings. So essentially, I want to look back more. So after we do this research for this 3 to 4 years, what's new in science, right, about this sub area, right? So are we just doing engineering, right? And the second thing is that if we can also look forward, right? So okay, we have doing a lot of things. What's lacking scientifically today? So we'll first talk about this reflection when we look back. So basically, if you look at this diagram, right? So my group is lucky enough to be the first to look into many of these pieces. But then today, in the security area, it's definitely not just us doing this. There are many, many more research also finding out different kind of attacks in self-driving cars scenario. And actually, this is it's a very recently did, and as you can see, this exponential trend, especially in the last 2 years in this area, right? A lot more research. And then this is actually only counting those commonly viewed top-tier conferences across security, AI, software engineering, robotics, right, computer vision. So, but then you just remember also there's a trend of this exponential growth of AI security, right? Generic AI security. AI is fundamentally vulnerable to adverse examples. So one question just pop up, right? When we do this survey. So is CPS AI security anything fundamentally different from generic AI security? So this is essentially what we find out, that this maybe actually can be viewed as a standalone subproblem space actually in AI security, which we can call it a semantic AI security, right? So this is basically a concept just brought up by us recently, and this is generalized from the semantic adversarial deep learning concepts by Professor Sanjay from UC Berkeley back in 2018. So basically, from our research, that we generalized that. So basically, it was mainly for deep learning and robustness, right, without any specific attack model, but then we generalized it to AI, from deep learning to AI, because it's not just like deep learning, but also program-based AI, like those planning logics, and also not just robustness, right? We show so many different attack models. So in this case, we generalized that concept to semantic AI security. So basically, what does the semantic mean is that this is essentially this whole vision being proposed by incorporating semantics. Because if you want to analyze this AI security analysis, well, if you want to do AI security analysis and also defense designs in the CPS context, we have to systematically integrate the semantics and also the context of the overall CPS, including the AI component, into this analysis process. And this actually incurs many new security challenges and new design challenges beyond the generic AI security challenges, right? You want to not only do generic AI security challenges, like you want to make it more efficient and more effective in optimization, you also need to further address general semantic gaps between AI component and system level security properties. And to see that, So let me just illustrate based on our experience so far. So remember this diagram, right? We want to attack this essentially this AI security, this autonomous AI stack. So here, if we look at this generic AI security, you usually just open one box, right? Just open one object detection, and I'll say, okay, we just study it. So this is essentially what they do is that they try to essentially this is what started from this 2013. So what you do is that you change the input, right, of this model, just change the input alone, introduce the delta X, and then you want to say, okay, whether I'm able to introduce a very big delta Y, right, in terms of the output. So this is a very famous example, right? I guess everyone doing AI security will use this as an example. So you add some noises, right? Add some noise into the input of this model, and then see whether you're able to trigger big delta Y, right? From, for example, Panda to Gibbon. But then if we look at this from the CPS perspective, like AI-enabled CPS, it's definitely far from just directly changing input and then directly using the output, right? Because in this case, there's a whole problem context, right? Whole system context enclosing it. So if you look at that, there are actually at least two general semantic gaps you can see. So one is that you somehow need to first go from the system level input space to the AI problem like input space, right? Like so basically, if you look at this in this case, so we call it system to AI semantic gaps, because if you look at this semantic problem space like constraints, right? If you want this system level attack vectors like laser shooting or changing the shape of this objects or changing the road surface, right? They're bounded by the semantic problem space constraints, like physical laws, road object size limit, and they are actually far from reaching arbitrary delta X, right? So basically means that somehow there's a very big gap between what you can do in the physical world, in this case, which is the semantic problem space, to what you can do at the AI input space, right? Definitely far from just directly adding the noises from there. So this is something fundamentally challenging due to a concept called inverse spatial mapping problem proposed by a previous work published in Oakland SMP. And then even if you're able to go from the system level problem space to the AI problem space, that's actually not enough, because not actually that's also the other side of the problem. Because even if you have a delta Y, you are not able to guarantee that all delta Y can cause a meaningful system level attack effect, right? Like vehicle crashes or land departure. And this is what we call the AI to system semantic gap. So there are many counterexamples people show that why this is a delta Y is non-trivial to cause system level effect, right? It could be the misdetected object is at a far distance for automatic emergency braking. It could be that the misdetection can be tolerated by some subsequent AI modules like object tracking. It could also be you need a continuous left frame like impact to have an end-to-end impact, right? So in this case, this is discovered from my own research, right? This is 30 patch one. So basically, in the land centering systems, if you just trigger one single frame attack, you can only lead to less than 0.3 millimeter lateral deviations at a normal speed, which is nothing, right? It doesn't really affect anything in terms of the lateral deviation. So it has to be continuous, but how to do that, right? Highly challenging because of driving dynamics and also closure control. Right, so basically, if you look at this, right, for a CPS AI security work to be semantically meaningful at the CPS system level, it must explicitly or implicitly address these two general semantic gaps. And if you look back at all these works, they all just doing one of their main challenges, or at least one of their main challenges, are about either system to AI or AI to system. And this is even more clear if you look at it, this works in my own group, right? So basically, one thing that we did a lot is trying to model this attack inputs, right? It's an object, or it's patch on the front car, or patch on the ground, object placement in the environment, right? And then this is essentially trying to address system to AI semantic gaps, right? So you want to map from the system level attack input space, like patching on the ground, on the side, 3D shape changes, object position angle changes to the AI model input space, right? As the pixel value changes, light point cloud changes. And then with that, it's not enough because we also have many other kind of research components. For example, you want to do simulation. You want to say, okay, whether we can actually cause a crash, whether we are actually being able to cause a denial of service. And then on the right, this is in a 30-row patch, we also did that specific alternative functions trying to bend the landlines, right? So this is actually trying to address the AI to system semantic gaps, right? From the AI component level errors, like perfect misdetected objects, bad land, to system level attack effect, right? Vehicle crashes, late departure, right? So basically, if you look at this, right, this complicated semantic context and also the new challenges brought by the semantic gaps scientifically differ CPS AI security from the generic AI security, right? And then for the last piece, I will look forward about what's scientifically lacking today. So basically, we did a survey in this domain, so feel free to look at it. I won't be able to talk too much into it due to the time limit. But then we have summarizing the status trend, and then we're also summarizing the critical scientific gaps. And we have, if you like, you can look at this SOK efforts. Right? We summarized 6 different gaps. So today, I will just highlight one of them, basically on the evaluation side. So basically, what we notice is that in this particular area, CPS AI security is widely recognized that in autonomous systems, AI component level errors do not necessarily lead to system level effect, right? So it's essentially the AI to system semantic gap. But if you look at all these works, right, they are all published in this widely recognized top tier venues across AI, security, computer vision, robotics. The vast majority, like 75% of them around, did not really perform any form of system level evaluation, right? They didn't evaluate with full stack AD system and exclusive control via either simulation at least or a real vehicle setup, right? But without it, it can lead to meaningless attack or defense progress at a system level. So, so this is a demo to show why this is super critical. Because so essentially, this is a prior work called Shifter, which is a very famous one in the software attack. But one thing you can recognize that this system is highly successful at a component level. Over 70% frame level success rate to make stop sign disappear, but they fail just substantially at system level. 0% stop sign violation rate due to the tracking process. And it's not just about it. It's also for other existing designs published in top tier places like CPS. And what this means is that just without system level evaluation, it's actually very hard to know how meaningful a proposed attack is from the end-to-end AD driving perspective. So for the interest of time, I won't talk about like the challenges about how to solve it. But in the end, we hope that a community level efforts can be used to build a common system level evaluation infrastructure. So we proposed a platform called PASS, Platform for Autonomous Driving, Security, and Safety, which envisioned to be an open, uniform, and extensible system-driven evaluation platform. We built a defense plugin as APIs, plug-and-play modular designs, standardized metrics, simulation-centric design, and also have some test vehicles for fidelity improvements. So yeah, so we are in the progress of soliciting community feedback. So yeah, if you like, definitely let us know. And we also have a website with all this information. And then this is about the autonomous driving side. And then we also want to emphasize that we also perform responsible disclosure, right, to companies, trigger them to have a vulnerability investigation. And then on the V2X side, also we also have some research, but then I won't go into details. Essentially, we try to we're actually the first to study the security and then build defense for infrastructure side of CV systems, V2X systems like traffic light, smart traffic light, and also we're the first to build a automatic vulnerability discovery process for V2X protocols such as tuning. We have actually reported and received the vulnerability acknowledgement from the newly discovered vulnerabilities from the HV 1609 working group, which is the standardization group. They plan to integrate some of the defenses to the next version. So to conclude, so basically, hopefully from this talk, I was able to see that my group is trying to be active in developing research space of CPS AI security. So currently, we focus mostly on the AD and intelligent transportation side, and this is the collection of our efforts. So personally, I believe this is only the beginning of this research problem space, because as you can see, we're mostly on the tech side. We definitely need more on the defense and research infrastructure side, like I said earlier. And then to facilitate the community building and broader impact, so I think this is also what Inzhi to talk about at the beginning. So I co-founded a workshop called AutoSep, which is actually become a symposium. So for the next year, and then yeah, feel free to look at it. And it's in the beautiful San Diego. So yeah, so maybe a good place to visit. And then we have a Twitter. If you can look at our kind of the progress. Also co-create DEF CON's first autonomous driving themed hacking competition, and then this is essentially DEF CON is one of the world's most famous hacking like the convention, like hackers to go there, and we created this autonomous driving hacking there. It's a simulation based, a lot of challenges for to create an attack or defense. And then this year we did the second time at Vegas. So DEF CON is always at Vegas, and this is the scoreboard and then the on-site view. And then yeah, stay tuned. We have hopefully we'll get a chance to do that for another year at DEF CON. And then also serve as the essentially on the focus group and the panel of NIST on the ADAI testing standards and the metrics. And then with that, I'll just thank all my sponsors, and then I'll be happy to take questions. Yeah, and then yeah, feel free to contact me also if you have questions.
Thank you, Dr. Chen. I think Tony, you have a question. You want to go ahead? I see a raised hand.
Yes, yes. Thank you, Alfred, for telling us about your really impressive portfolio of work. My question is, can you summarize the list of attack mechanisms that you've studied? You know, there's GPS spoofing, there's patching, there's adding objects to the landscape, and GPS borders on sort of is more intrusive. But are there other exploits? You know, summarize the ones that you talked about today, and also what are some of the other ones that you're looking at?
That's a very good question. So I think yeah, let me just make it clear. Okay, so basically there are two, I think, the general and fundamental attack surface that I think. So one is the sensor attack, another one is the physical world attack. So basically, the sensor attack is the one that basically uses GPS spoofing, also have LiDAR spoofing, that's also camera blending, also for radar, have radar spoofing. So I mean, you can use ultrasonic to attack it. So there's actually in the security community, a lot of sensor attacks being discovered. And on the other side, what is that about this landscape? It's about physical attacks that I think. So basically, you can change the looking of the road surface, of the signs, the front cars. You can also change the shape, right? Essentially, the texture and the shape. Essentially, these are the two categories of attack vectors that I usually use in my attack model.
Okay, so you're not taking advantage of infiltrating the system through a wireless channel, for example, like others have done in the past. Is that correct?
Yeah, so far, yes. And then I think that's a very interesting attack vector. It's just for now, this kind of systems like autonomous driving cars are not that connected. So they are basically just mainly connected to their own backend cloud, and then not really yet talking to other people, and then not have a general wireless attack surface. I mean wireless this connectivity, and then and also those may not be fundamental, meaning that if you have this if you're hacking this wireless this surface, it may not give you control, right? Because it may not be a critical component. But as sensing, because self-driving cars or essentially this autonomous AI are data driven, so data path is more fundamental and also more general, I think, in terms of the security and that purpose. Yeah, that's why I start with that. But then server attack is also something I look into more on the second part of my research. But then just now, the V2X or connected vehicle set is not that well developed in the real world. That's why this autonomy stack, so security I consider more is on the physical layer attacks.
Great.
And
Thank
then,
you.
and then,
Yeah.
yes, but then that's a very good question, because I actually started to look at that in recent, in actually this year. So because I talked to DMV, so DMV is like the transportation kind of department at California, so they regulate the autonomous vehicle testing. So they are actually asking about this. How about this remote operator channel, right? Because you know as the technology kind of advanced, people realize that we cannot really just purely rely on the essentially the onboard sensing or onboard like driver. So so they start to do this remote control center. So if there's some problem, then they fall back to the remote operator. But in that case, it's actually an end-to-end and a very powerful attack vector if you're able to compromise that channel. But then we are now looking for a concrete example to study about that remote that channel, because that's not this, we cannot see a public standards so far.
Thank you very much.
Sure. Anybody else on the panelists have question? We got about 2 minutes. I don't see any raised hand, but I have a question, Dr. Chen. Have you looked into the false positive part? I mean, sometimes you think this is an attack. Have you looked into those aspects at all?
Very good question. Very good question. So actually, so in the physical layer attacks, especially the physical order ones. So let me actually jump there. So I think it will be even more clear. So for sensor attacks, actually, it's rarely to have false positives, because the sensor artifacts are not supposed to happen very regularly. So in the real world, but then physical attacks is different. So essentially, this is like a sensor is all correct, but then we try to find corner cases in the driving context. So in this particular case, actually there are many. These corner cases can happen even without attack. It's just they commonly happen. For example, for this rock case, there are some videos showing that Tesla cannot see a rock, and it just crashed into it, and then the driver got panicked. And also for the I think so that's a case for this it's actually not here, but then there's a case. So actually we use physical environments trying to fix an attack vector. Then we find out that when we apply it to the non-attack case, like in that case, the accuracy actually improved, because we helped them to solve some of the false positives actually that their model wasn't be able to learn in the first place. So yeah, so I think many of this like especially for the AI corner case aspects, many of them are false positives. They just in the training process they didn't encounter.
Right. Thank you. I know we're running out of time, but I'd like to acknowledge one question from the Zoom. So many thanks for such a comprehensive set of research. I'm used to thinking of actions like lane changing as a product of a decision model, taking uncertainties into account. Security issues here play a role similar to data challenges, things like missing data, bias, etc. in analysis of real-world data. The question is, how does your semantic approach jibe with such quantitative needs? Yeah,
that's actually a very good question. So actually, I had a research actually that was actually ongoing. We published in IB, a conference called Intelligent Vehicle, that we actually try to design an uncertainty-based controller. So because so this is driven by the attack, because we find out that so that's actually for the study through patch ones. So when the model, then the left-hand model see this ones, they actually have a bump up in terms of the uncertainty in terms of the model. The model also is less confident. But then previously the controller is disconnected with the earlier parts, like the or it doesn't have a very integrated design with the the model. So the controller part didn't really realize about this uncertainty. So then afterwards we design a kind of uncertainty-based controller. Basically, like when uncertainty is high, we just try to slow down more, and also try to only drive in the essentially the safe more safe like regions based on the uncertainty bound. And then when uncertainty is low, that we just drive more. So yeah, it actually works well.
Excellent.
So I think uncertainty is a very good aspect. Yeah. Sure.
I have a question from panelist Ken. Unfortunately, has audio problem. The question is: would you what simulator did you use, and what simulator might be best for platform that you are proposing? The simulator.
Very good question. Very good question. So at this point, we are using LGS which is which is actually it used to be the commercial one, but now it's sunsetting. I guess the LG seems to be I guess ditching this line of the work now. But then I think we also tried Color, which is also good. So these are the two open source ones. But then from my point of view, I think no single simulator is good enough because we always see fidelity like problems. So but then the simulation-based approach is the only way to scale up this research to the community level because we cannot require everyone to buy a car, right? So then in this case, so first of all, so we want to support both simulators in our platform so that if the results are consistent, then we have more confidence. Sure. Then the second thing is that there are more recent approaches trying to improve the simulator fidelity. Essentially, the main fidelity of the problem is on the sensor noise modeling. So the sensing information, sensing data in the simulator are too perfect. So people are trying to introduce kind of noises. So essentially, that's also something can help with the fidelity. So, but yeah, I think that's probably the only way to go. Yeah.
Excellent. Thank you for. I know we went a little overboard on time, but excellent presentation and good to see how the system-specific research is helping V2X type work. At least one of your work, right? I'd love to come and visit your lab when I'm in that neighborhood. If anybody else has any more questions, I'd like to thank Dr. Chen for giving a very insightful talk. I know Inji had to drop. I think we should thank you the audience and thank you everybody for joining and participating in this talk. Unless anybody from the panelists have any question, we'd like to conclude this talk officially. And I know we're going to talk to you in a minute or so.
Thank you. Thanks, Alfred.
Yeah. See you, everybody.
Good talk.
Yeah.
Thank you.